Welcome back, class. Whitlock and Schluter Chapter 11, Inference for a Normal Population. This is going to be focusing in on confidence intervals and t-tests for a single normal. We'll focus in on the confidence interval first. Okay, as we're going into it, I want to just remind us of Romans 1:20. Since the creation of the world, God's invisible attributes, His eternal power and divine nature have been clearly seen through what has been made. This is where we start to see how that bell curve, which is an imprint of His nature upon the world, manifests itself. So watch for it. Okay, we're going to start off here with a thing called the student's t-distribution. Now, what we had last time was x bar is approximately normal. Okay, that being the case, we're going to dig a little bit deeper. If you took your x bar and you converted it into a z, then that would look like x bar minus the true mean divided by sigma over rad n, that is the standard error, is approximately normal with mean zero standard deviation, or you could say standard error of 1. Okay, now in practice we often don't have this guy right here, standard deviation. What we do wind up doing is we estimate the population standard deviation with a sample standard deviation right here. When we do that, we now have more variation in the statistic. So we call that capital T instead of capital Z. And it turns out that this capital T has a distribution which can be computed. And it has come to be called the student's t-distribution. And I will discuss a little bit of the fun story behind that in class. But for now, student's t-distribution, and it has one parameter. That parameter is called degrees of freedom. Degrees of freedom. Okay. It's typically abbreviated with DF. And in this case, it's n minus 1. Sample size minus 1. Okay, let's talk a little bit about student's t-distribution. So, if the black curve is normal, I'm going to draw it large here, then the student's t-distribution is what I call the wannabe normal. It is like the normal, except that it has more probability in the tails and less in the middle. We call it a fat-tailed distribution. So I'm going to sketch out a curve here. It's got fat tails. And let's just suppose that the sample size were 11. Let's say it's 11. That'll give us a degrees of freedom equals 10. Let's do another one here. This one has more degrees of freedom. You can see that its tails are still fatter than normal, but not as fat as the degrees of freedom 10 curve. So we'll say it has a sample size 21, degrees of freedom 20, and we'll do one more, degrees of freedom 30, and with that 30, we're starting to get pretty close to the normal distribution. I'm just kind of sketching it in here so you can get the idea of how this thing plays out. Therefore, once n is large enough, then the distribution is itself normally distributed. Key assumption on this process is that x is normal. X is the parent. So in order for this process to occur, where the statistic t follows the student's t-distribution, the parent is normal. Now, if that assumption is violated, then it turns out to be robust to violations of that distribution. And we'll also discuss that in class. The t-distribution is bell-shaped, symmetric about the mean. The mean equals the median and the mode, just as the normal distribution. Okay, we've talked about its notation, and we're going to use it for 1 and 2 sample hypothesis tests and confidence intervals. Okay, as far as assumptions, we'll recap those. Data come from a random sample, and the parent is normally distributed.